Our final talk of the session will be presented by Mark Mueller.
Good morning, all. It's my great pleasure to present to you our joint work on PRIMA, a general and precise neural network certification framework leveraging scalable convex approximations. So, neural networks have achieved exceptional performance over the last years when evaluated on standard test sets, often even exceeding human-level performance. However, they exhibit an alarming lack of trustworthiness. We've already seen pandas being classified to gibbons and stop signs misclassified, so I'll show you another stop sign example. Consider an autonomous driving setting where we train a neural network to detect and classify street signs. In the upmost row, we see a stop sign from our test set, which is then indeed classified correctly as a stop sign by our trained neural network. If you now, however, rotate this image by exactly the right amount, it's suddenly misclassified as a turn left sign. Even more alarmingly, perhaps, if you partially occlude it using stickers or graffiti, it's classified as a 120 kph sign. As you might imagine, this is not ideal if we apply such a system or deploy such a system in a real-world autonomous driving setting. This, in fact, extends far beyond robustness properties and autonomous driving. In general, whenever AI systems have a significant impact on human lives, standard accuracy is not enough, especially we as PL people want provable guarantees. We want certifiably trustworthy AI if we want to apply it for any kind of important decision-making. This brings me to my problem statement, neural network verification. Consider the problem where we have some precondition over network inputs and the trained neural network that we wish to analyze. And now our task is to prove that for all inputs that satisfy this precondition, a postcondition, typically only over the network outputs, is also satisfied. However, this problem, unfortunately, is undecidable for the general case of general networks and general preconditions. Therefore, we need to over-abstract, in our case, using abstract interpretation. We encode the precondition as a convex abstraction, and then we propagate this abstraction through the neural network, in this case illustrated as just one linear and one nonlinear layer each, despite us having typically many more. We thus obtain a convex over-approximation of the network outputs. This allows us to then reason over a postcondition. Let me give you a slightly more concrete example. Let's consider the input image of the digit 8 in the upper right-hand corner. And now we wish to verify that we can perturb every pixel value, every pixel intensity individually by an epsilon amount and still obtain the right classification. We can encode this by saying every input in the induced hyperbox that is illustrated below should be classified to the same class. This classification to the same class corresponds to saying the argmax over the outputs of the neural network should be the same for all these inputs. We can equivalently state the problem as the minimum over these inputs of the difference between the output corresponding to the target class and all the other classes should be greater than 0. Unfortunately, this optimization problem is very hard to solve because the underlying neural network is non-convex and highly nonlinear. So what we can do is derive a lower bound to this objective using abstract interpretation. For example, if we derive an abstraction of the network output in polyhedra form, we can use its constraints to encode this as a linear problem, which is then very easy to solve. An additional advantage of this approach is that we can add additional constraints to further refine this abstraction and derive a more precise analysis. So what is the remaining challenge? Most existing verifiers can certify the linear layers of the neural network exactly. However, the nonlinear layers remain challenging. There, the abstractions introduce imprecisions which accumulate over the network and can grow exponentially with the network depth. So the challenge really is to devise abstractions for the nonlinear activation functions that are precise and yet scalable enough to scale to the network sizes of many hundreds of thousands of neurons. This is actually an extremely active research field with around 200 publications per year over the last couple of years, of which I just show a small selection here. And as I said, the general approach or the general metric is to obtain as precise as possible analysis within reasonable runtime. This is shown here on the right-hand side, where we show the certified accuracy, so roughly the portion of properties that we're able to prove over the mean time per property. As you can see, our work, PRIMA, achieves a very high accuracy, a very high precision at a quite reasonable runtime. Before I go into more detail about how PRIMA works, I want to introduce you quite generally to how we abstract nonlinearities. Let's consider the popular ReLU function defined as the maximum of 0 and some input x, and consider the case where we have some predetermined lower and upper bounds to the input interval Lx and Ux respectively. Now we can compute a convex abstraction of the ReLU function over this interval as its convex hull, which can be easily encoded using free linear constraints or linear inequalities, as shown on the right-hand side. However, neural networks do not typically include only individual activation functions, but whole layers of hundreds or even thousands of nonlinearities. Here we consider a toy example of just four activation functions in a layer. We can now encode those by applying the same per neuron relaxation to all of these individually, and then thus obtain a relatively loose abstraction of the whole layer. This was still believed for a while to be the tightest possible convex relaxation, and is thus called the single neuron convex relaxation barrier. However, actually, we can obtain a much tighter abstraction if we abstract all neurons or all nonlinearities in a layer jointly. However, unfortunately, this has exponential complexity in the number of neurons, and is thus intractable. In prior work, we went one step in this direction by forming small groups of neurons and abstracting those jointly. However, this still relies on an expensive exact convex hull computation method. Thus, this approach was limited to only considering few and disjunct neuron groups, which only capture few interdependencies between the neurons. In this work, we propose to use a novel approximate polynomial time convex hull computation method, which allows us to consider many more such neuron groups, and thus capture more complex interdependencies between the neurons, and thus derive a much more precise analysis. This approach relies on two key factors. First, an efficient and general approach to computing multi-neuron constraints or abstractions for almost arbitrary activation functions. And then second, an approximate polynomial time convex hull approximation computation method that is leveraged by our multi-neuron abstraction. In general, we compute multi-neuron abstractions for whole groups of neurons as follows. Consider the case where we have a group of two neurons with the inputs x1 and x2. We have the input space, as shown here on the left, as a blue diamond. We now partition this input space into much smaller regions, here by intersecting with the quadrants. And then on these smaller regions, we bound the outputs of all the activation functions very tightly. This yields then polyhedra in the input-output space of this neuron group. By now computing the convex hull over these bounded polyhedra, we obtain a tight abstraction of the whole neuron group jointly. We can now extract the inequalities defining this polyhedron and add those as constraints to our LP encoding the verification problem to derive a much more precise analysis. Let's consider, again, the ReLU function. If we have to abstract it on the whole interval from the lower bound to the upper bound, we need to introduce this triangle relaxation where effectively all of the blue area corresponds to an imprecision we introduce. However, if we now split the interval at x equals 0, we can encode it exactly on the two resulting intervals, either as y equals 0 or as y equals x. But this can be applied much more generally, even for non-piecewise linear functions. Consider the sigmoid function on the lower left-hand side. Here we can simply split the interval at an arbitrary point c, and then derive tight linear bounds on the two resulting intervals. Otherwise, the approach works exactly the same. We can even extend this to multivariate activation functions, where we split the input domain, again, into smaller regions. For the max pool function that's illustrated here on the right, we simply split the input space into the regions where one of the inputs dominates. So, for example, x2 greater equal x1 and x1 greater x2. On the corresponding regions, we can then again bound the outputs exactly using y equal x2 and y equal x1 respectively. So this is in general somewhat similar to prior work ReLU, but there's one crucial difference. By cleverly choosing when to extend the dimensionality of the polyhedra and when to compute convex hulls, and for the details I refer you to our paper, we can significantly reduce the number of convex hulls that we have to compute in a high-dimensional space. Where for the popular setting of ReLU groups of size 3, ReLU needed to compute 7 6-dimensional convex hulls. We only need to compute 1 6-dimensional convex hulls, with the other convex hulls being computed in lower dimensional spaces. with exact convex Hull computation methods, this already reduces the required time, but it's still quite slow. So we propose to use a novel polynomial time approximate convex Hull computation method. Before I go into more detail, let me quickly give you an outline of duals, this time duals of polyhedra and not numbers. For our intents and purposes here, it suffices to know that for the representation of polyhedra that we have, it's easy and computationally cheap to translate from primal to dual space and vice versa. The key property here is that an over-approximate convex hull in primal space corresponds to an under-approximate intersection in dual space. This is what we leverage in our approach. We first translate our polyhedra from primal to dual space. Then in dual space, we compute an under-approximate intersection, which we can then translate back to primal space to obtain an over-approximate and thus sound approximation of the convex hull. Before I go into yet again a bit more detail, let me quickly introduce the polyhedra representations. We can represent a polyhedron either by the constraints that define the supporting half spaces. This is called the H representation, or we can describe the exact same polyhedron by the generating set of its extremal vertices. This is called the V representation. Typically, or quite often, we maintain both representations. This is then called double description. We relax this to the partial double description, where we maintain the exact H representation, but you choose an under-approximate vertex representation. That is, we simply require for all vertices in our vertex representation to satisfy all the constraints of the H representation. Now let me first quickly explain how we can compute exact intersections, and then how we relax this process. To compute exact intersections of polyhedra, we take one original polyhedra and then sequentially add all constraints of the other polyhedra to it. This works as follows. Here we illustrate the original polyhedron in green, and just as an example, just add 3 constraints illustrated in blue. Let's consider the first step. We add 1 constraint to our original polyhedron, and for every of its vertices, we decide whether or not they satisfy these newly added constraints. The vertices that satisfy the constraint are marked in black and the others in red. We now shoot rays from all the black vertices to all the red vertices. You can think of this of all the vertices inside the other polyhedron to outside the other polyhedron. And now we compute the intersection of all these rays with the newly added constraints, or rather the corresponding hyperplane. These are marked in blue here. We can now obtain the intersected polyhedron by taking the union of the black points and the blue points. We repeat this 2 more times to obtain the exact intersection. As you can see, this introduces quite a large number of points that we then later remove due to redundancy. Note that here in this 2-dimensional example, we ever only add 2 new points. However, in higher dimensional spaces, we can add arbitrarily more points. We instead propose to add all the constraints in the single step instead of sequentially. This leads to discovery of wave fewer points, but works quite similar. We again check for all points of the original polyhedron whether they satisfy all the newly added constraints. Again, mark those black, and mark the vertices that do not satisfy at least 1 constraint in red. We again shoot rays from all the black to all the red vertices and compute the first intersection with any of the newly added constraints. Note that we discover way fewer vertices, but we also miss 1 vertex, 1 extremal vertex of the exact intersection, here marked in yellow. We thus only obtain a slightly under-approximate intersection, here shown on the lower right. Note, however, that this process is asymmetric, and we can use this to boost the precision of our approach. Here, consider the example where we have on the left-hand side 2 polyhedra where the exact H representation is in black, and the under-approximate vertex representations of our partial double description are in red and green. We can now compute our batch intersection in both directions, yielding the results shown in the 2nd and 3rd column. Note that if we now take the union of the thus-discovered vertices, shown in the 4th column, we actually recover the exact intersection of the exact H representations, despite neither of the original vertex representations covering this whole intersection. This is the key to the precision of our method. To put it all together, we define the partial double description method as our approximate convex Hull computation method by first translating our original polyhedra from primal to dual space, then adding the constraints of one to the other, in a symmetric fashion. Doing the ray shooting and the vertex discovery, combining all these vertices, removing redundant vertices, for which I also refer you to our paper, before then translating the thus obtained under-approximate intersection back to primal space, where we then have an over-approximate convex hull approximation. Note that this is quite general and not only limited to neural network verification. In fact, this approach is exact for small dimensions. This is for up to 3-dimensional general polyhedra or up to 4-dimensional polyhedral cones. Also, this has polynomial complexity. To be more precise, it's quartic in the number of input constraints and linear in the number of input vertices. This is in contrast to an exponential complexity in the dimensionality of the polyhedra for the exact method. So, how do we integrate this into a neural network verification approach? As I said, we typically encounter very large layers of nonlinear activations. So we decompose those large layers into smaller groups. And for each of these groups, we over-approximate the input space. And then, given these input polyhedra after the splitting, as I just described earlier, we compute the multi-neuron abstractions. Then we abstract the inequalities describing the obtained polyhedron and refine our LP encoding the verification problem this way. This allows us to certify many more properties than we could without these added constraints. So how does this perform empirically? Let us first simply look at the approximate convex hull computation method in isolation. On the left-hand side, we see the normalized volume over the percentile of problems that we typically encounter during neural network verification. In orange, we see our method, PRIMA. And as you can see, for most of the properties, there's almost no difference between the exact and our approximate convex hulls in terms of their volume. On average, we only observe a 5% volume increase for the cases that we encounter here. This is in contrast to roughly 300% larger volume that we would obtain using just the constraints discovered with single neuron abstractions. All the while, as you can see on the right-hand side, where we show the speed up over the percentile, we are much faster than using the exact method. In fact, this realizes a roughly 200-fold speed up. So how can we translate this into verification performance? Here we look at the quite popular L-infinity robustness property for a wide range of networks, both on MNIST and Cypher10. I've marked 2 of the examples. Here on the upper example on MNIST for conv small, we see that we certify roughly 50% more properties than either of the competing methods. Here we compare against K-Poly, the prior work, which used exact convex hulls, and opt-C2V, which is a different approach to also computing multi-neuron relaxations. Note that we are still faster than either of these 2 other methods. For another example on Cypher10, again for conv small, we see that we verify roughly 12% more properties, but are 5 times faster than either of the other methods. Note further that this scales to relatively large networks, here of up to 100,000 neurons, and that the analysis time does not necessarily directly depend just on the network size, but also very much on the properties. For example, the relatively small conv small takes around 50 seconds per sample to analyze, which the 10 times larger conv big that is trained specifically for analysis can be analyzed on average 1/10 of the time. However, this is not limited to these, what is by some considered toy problems, but can also be applied to the real world. Here we look at the verification of an autonomous driving setting, and more precisely at the Udacity autonomous driving dataset for steering angle prediction. We take a CNN architecture proposed by NVIDIA with roughly 100,000 neurons and 27 million connections in 8 layers. Here we consider inputs that are roughly 20 times the size of the popular Cypher10, and again certify robustness to L-infinity norm perturbations. On the right-hand side, we illustrate 2 samples or 2 images of this dataset. In blue, you can see the certified, or shaded in blue, you can see the certified region of possible steering angles as obtained with PRIMA. Marked in blue is the prediction of the unperturbed image by our network, and in green is the actual target. With red, we show the empirical bounds computed using adversarial attacks to the steering angles. As you can see, in both images, the actual error of the standard prediction, so the prediction on the unperturbed image, is quite similar. Whereas the subjectively much worse image on the bottom, where the contrast is much lower, the certified region. So our robustness or confidence is much smaller. This again highlights the importance of obtaining these robustness guarantees, or at least doing a robustness analysis to actually evaluate how well our network performs in real-world conditions. So to summarize what I've told you today, I've introduced the split-bound lift method, a general approach to computing multi-neuron abstractions for almost arbitrary activation functions, the partial double description method, a general convex hull approximation method with polynomial complexity that's also of interest outside of neural network verification, then how we combine those in our verification framework PRIMA, which realizes state-of-the-art results. If you have any questions, I'm more than happy to answer them now. If you want to take a look at the code or play around with it, you're my guest to do so. It's available on GitHub. And otherwise, I thank you all very much for your attention.
Thanks, Mark. Do we have any questions in the audience here? If you're online, again, I recommend putting those questions in the Q&A tab.
I think we do have a question in the room.
Okay, fantastic.
Hi, thanks, Mark, for the great talk. I'm curious if you thought about putting a probability distribution on this convex hull, because maybe the region is not evenly populated by semantically meaningful inputs, or the error in certain regions is higher than in others. I was wondering maybe if you could speculate on possible improvements to this work that would incorporate the notion of a distribution over this hull. Thanks.
That's an excellent question. So in generally, we distinguish a bit between two different kinds of guarantees that we can obtain. We can either obtain deterministic guarantees, as we do here, where we say there exists no point that's set in the precondition that violates our property. So for these cases, we typically do not use any distributions because we really want to guarantee about all points, regardless how unlikely they are. However, there's a different class of guarantees that provide statistic guarantees, where we actually draw from a distribution of inputs and then just make a probabilistic statement about the portion of those that classified correctly. And from this, we can then obtain probabilistic guarantees that say with a confidence of 99.99%, there will be no sample in this region that will lead to a misclassification. If you're interested in work, I suggest you can look into randomized smoothing. There's a variety of, or there's also a lot of work in this space.
Do we have any other questions? If not, I think people are hungry, so let's thank our speaker and get some lunch.